stress X is equal to mz over izz multiplied by y. Okay, so for this case is, so this is moment about z. Okay, so we want to find izz. So this is our width. So this is for a moment about z. Okay, and this will be our depth. Okay, because the axis of interest is our what? Our ZZ axis. Okay. Now, what if now, okay, what if now we decide to change? Okay, now the moment is applied about y. Okay, now the moment is applied about y. Okay, so we're gonna change this to moment to apply in the y direction. Okay. So I'll try to, now I will draw even number. Okay, drawing odd number. So this is 6. So this is steel. Okay. This is also steel. And this is also. All right. Okay. So now we are going to look at moment about y. All right. So this is steel, brass. Right. So now question for you, if it's moment about y, which is our width now? Right. So if we look at the formula, stress X is equal to moment about y over I multiplied by z. Hey, when I say I write IZZ. Come on. So this is your I what? YY. So your YY axis now is here, right? Right. Now this become your what? Width. This become your what? Depth. Yes or no? Right? So the width now will change. Now some of you, okay, now draw me. Draw for me. How will this look like? Yes or no? So again, the depth will not change. So the first one is the brass and steel, okay, are still in the same width. Okay, so now it looks like this. So this is steel, right? The height, the depth did not change, okay, or the height. This is still the same, right? So now the brass become what? Has the width have to change to half, right? So now this is how the brass will look like. So now the material, okay, okay. Now the material will look like this. So this is steel, steel. Hey, why do I put? Oh God! Hey, come on. So there is steel. Okay, steel, steel. So now it's brass equivalent to steel. Okay, brass equivalent to steel. Does that make sense? Yes or no? Right? The depth is still what? The depth is still constant. So the last case where we were going to look at, okay, so you ask, okay, Eugene, now what if brass is held constant? So I'm going to draw brass is held constant. I'll try to eyeball that we are, okay, now I'm trying to make sure that, so now brass is still held, now brass is the reference material, so it's held constant. Okay. Okay. So this is our brass, is the reference material. So what will happen now is the steel increase in what? Thickness. right? So these two are the steel, right? Uh, are the steel equivalent to what? Brass. Okay. Does that make sense now? Who were asking that question? Someone, and it's a good question. Okay. By the way, so yeah, Curtis, does that make sense now, Curtis? Yes. Okay. So it's a good question. Okay. So again, what you see now down here is the what? Is the width that changes, the height did not change. Okay, so that is the only, this is really important. Okay, why? As I said, it is because of mathematically. Okay, mathematically this is important. Okay, so I will not confuse you. This is not valid. I will write this is not valid. Okay, I don't want you to apply the wrong formula. Okay, right, that's all the theory we're going to do. Okay, so we are going to do an example. Okay, we're going to do an example. So as I said, remember, what is changing is the what? It is the width. The depth did not change at all. Okay, so let's look at an example. By the way, all these examples that I'm putting up, this morning I put the image on Avenue to Learn. Okay, so you can get all these images on Avenue to Learn. Okay, let's look at this example. Okay, so this is our example number 1. So we have a top plate that is made of aluminum. Okay, 2014 T6. So this top part is made of aluminum. Okay, T6, and it's used to reinforce Kevlar 49 plastic beam. So the rest of it, so based on the shading, you can see, so this part, and this part, they are made of Kevlar. Okay, so determine the maximum stress. Okay, determine the maximum stress in the aluminum and in the Kevlar if the beam is subjected to a moment of 900 pound-feet. Okay, so the units over here is in feet. Later on, we need to do some changes. Okay, so based on the moment arrow, again, exactly like how I taught you guys. Okay, so based on the moment vector, as you can see over here, right? So that is our moment. So let me draw our transformation first. Okay, so this is our x, y, and this is our z. Okay, so we know that the moment over here, the moment is about the z-axis. Okay, the moment is about z-axis, and it's 900 pound-feet. And to change to inches, we have to change to inches because all our geometries are in what? Inches. Okay, so 900 multiplied by 12. So this will be equal to 10800 pound. Now is in inches. Okay, so we know based on the moment vector, right? So based on the moment vector over here, we know that above the neutral axis, sorry, centroid. Okay, I changed my, above the centroid, it'll be in compression. Below is going to be in tensile. Okay, nothing changes at all. Okay, right? What I taught you in analysis is still the same. You can apply it for anything. Okay, still the same. So you don't see this now. So I got from a handbook. Okay, or you will be, if a term test this question given. So we have Young's modulus of aluminum is equal to 10.6 times 10 to the power 3 psi. Okay, and then the Young's modulus of Kevlar, which is equal to 19.0 times 10 to the power 3 psi. Okay, we have that, right? So now the formula that we're going to use is equal to stress X, right? It's equal to, so we have a coefficient. So the moment is in Z direction, divided by IZZ, multiplied by Y. Okay, so we're going to apply this formula. So for this case, I'm going to pick, okay, we're going to pick, so I decide to pick the reference material. Okay, we decide to put the reference material to be aluminum. Listen, if you want to make it equal to Kevlar, answer will be the same. Okay, I just pick aluminum. Okay, you pick Kevlar, aluminum. Okay, the final answer has to be the same. If it's different, something is wrong. Okay, something is wrong. Okay, so as I said, the material we decide to put for aluminum. Okay, so N aluminum. Okay, so this will be Young's modulus of aluminum divided by the reference material, which is so aluminum. So this is 1. Okay, then we have N of Kevlar is equal to Young's modulus of Kevlar divided by Young's modulus of aluminum. So this will be 19, okay, times 10 to the power 3 divided by...
Eugene.
Yes.
Can you make the reference material, like, can you choose which one is the reference material? Does it matter?
Yeah, you decide. You choose Kevlar, the answer will be the same. Okay, does not matter at all. Okay.
Thank you.
Okay, does not matter at all. Okay, don't always choose the metal. Okay, you whatever you're happy you choose. Okay. So 19 divided by 10.6. So this is equal to 95 over 53. Okay. So in order to apply this formula over here, right? In order to apply this formula over here, right? So what we realize is based on this structure, right? Based on the structure that we have, okay, there are things that we have to do. We have to find the what? Centroid. Right? We don't know where the centroid now is. Okay. Now the centroid is based on your reference material. Okay, the centroid is based on your reference material. And I think the centroid will not change whether you take aluminum or Kevlar. Let me see later on, okay, how will it change? Okay, for now where I sit, I don't see how it will change because the depth did not change at all. Okay, now then we are going to find, after that, then we're going to find, okay, the second moment of area. As we know, in the second moment of area, it's only the width has changed, right? Due to N. So now the formula changes. Okay, so now it becomes NW multiplied by D cubed 12 plus by NW multiplied by D Y bar minus small y bar squared. Okay, so now we're going to find the second moment of area. Okay, so before I go on, I will make a small sketch what is going on now. Okay, I'll do a small sketch. Okay, a simple sketch, not small sketch. So we have a material. Okay, I'm not drawing to scale, okay, by the way. Okay, we have a material down here. Okay, so the material is in such a sense that it's like this now. All right, so this is the original.